Suppose that you're giving a set of points depicting an object, such as this one. If you draw all the points, then you are able to see both front facial features, for instance, this car, and the hairdo, which is at the back of the feature, which might be confusing. Given a viewpoint, we'd like to find an operator that will compute only the visible points. For instance, this is the result we wish to get. One way to compute visibility of a point set is to reconstruct the surface and then determine visibility on the reconstructed surface. However, reconstruction is a difficult problem both in theory and in practice, as we saw today, and it often requires additional information such as normals and sufficiently dense input. The key question that this paper attempts to answer is whether visibility can be extracted directly from the point cloud. Evidently, points cannot occlude each other unless they accidentally fall on the same ray from the viewpoint. However, once we reconstruct the surface, it is possible to extract visibility. And this implies that the point cloud inherently contains information regarding visibility. And the challenge is to extract this information. So this work is at the crossroads of three fields in graphics. The first is visibility, which has been a basic problem in graphics from its early days. However, most of the work in this field addressed visibility between polygons. While our goal is different, we would like to determine visibility of the points should the surface they are sampled from existed. The second area is point-based graphics. Here, visibility was addressed mainly within rendering, often while ray tracing. And the most common approach is to splat the points into the Z buffer. We would like to extract visibility regardless of rendering. And the third issue is surface reconstruction. We've already seen the connection, the relation to this field, and we'll get back to this later in the talk. So let's define a problem formally. We're giving a set of points P, which is considered to be a sampling of a continuous surface. And we're giving a viewpoint C. We'd like to determine for every point in P whether it's visible from C. However, we have a much longer wish list from the operator we wish to find. We'd like the operator to be correct in the limit. In other words, if all the points of the surface are given, we'd like the operator to mark a point visible if and only if it is indeed visible. And we'd like to give some theoretical guarantees for the more practical case of sampling. We'd like to avoid computing normals. The asymptotic complexity as well as the running time should be reasonable, even in software. The operator should be simple, and it should work for sparse as well as dense point clouds. So what I'm going to do today, I'm going to first present this operator. We call it the HPR operator, hidden point removal operator. I'll describe the operator, give a little bit of intuition, and then some of the theoretical results that we have. And then in the second part, I'm going to present three applications of this operator, applications to visualization, to view-dependent reconstruction, and to shadow casting. So let's start with the operator. Our operator consists of two stages, spherical inversion and convex hull construction. So during spherical inversion, we assume that we associate with the points a coordinate system where the viewpoint C is at the origin, and we map every point P along a ray from C to P such as this mapping is monotonically decreasing in the norm. Once we perform this spherical inversion, we compute the convex hull of the transformed set of points union C, the viewpoint. So even before I explain what this spherical inversion means, we can already make a couple of observations. The first revealing observation is that what this operator is doing is a simple reduction of the problem of visibility to the problem of convex hull construction, because all we're doing is a simple transformation and then computing the convex hull. The second observation is that the complexity of the operator is order of n log n in 2 and 3 dimensions. That is, the first step is linear, and the second step takes us in 2 and 3 dimensions, order of n log n, but this operator can be extended to any dimension we wish, and it's going to take us as much as the construction of the convex hull in the particular dimension. So let's focus now on spherical inversion, which is the only step that requires some explanation. There are various ways to perform spherical inversions, and in fact, in the paper, we mention a couple of families of inversions. But today, I'm going to discuss only one such family for which we ran our experiments and for which we proved our theorems. So we call this, this inversion spherical flipping. In essence, what this spherical flipping is doing, it's taking points internal to some bounding sphere and projects every point internal to the sphere to its image, which is external to the sphere, using this equation. If we look at this example, what spherical flipping does, it's taking the blue curve, this is our input, which is constrained to be bounded in some green circle, which is centered at the origin, our viewpoint. And we map it to its image that you see here in red. This is the result of spherical flipping. Then we compute the convex hull, and you see here the convex hull. And when we project the convex hull back to the original input, this is what you see here to the right, then we get the points visible from a viewpoint. So the main result of this paper is the claim that these points that lie on the convex hull of the transformed set of points amounts to determining the visible points. And just to further convince you that the operator is really, really simple, this is the MATLAB code that implements the operator, and you see that it's very short. It consists of n lines of code. Of course, one of the lines is a serious one, is the computation of the convex hull. But you get it in MATLAB for free. So, so this is the operator. Let me give you a very brief intuition. So we're looking for points whose image lies on the convex hull. So let's look at a point that without loss of generality, this is in polar coordinates, and without loss of generality, let's assume that our point pi lies on the x-axis. And we're looking for the points that would lie on the convex hull after applying spherical flipping. So we're looking at points pi hat and at a line L hat that passes through this point and creates an angle beta with the x-axis. We'd like to find the source of this line, that is, the curve that is transformed using spherical flipping to this line. And it turns out that this curve that you see here, L, can be described by this formula. If we look more closely at this curve, we can see how the shape and size of L changes as a function of the angle beta, the angle that the line L hat creates with the x-axis. So we see that the smaller beta is, the larger the area that is bounded by this curve L. And we said that L determines the empty region that is associated with the point pi. And in essence, what we have for every point pi, we have two special points, pj and pk, that define the empty region associated with a point pi. So to say that a point is visible, we'd like to say that this area that is bounded is large enough. So the amount of visibility is determined by the size of this curve. Or in other words, what we need to set is a visibility condition on the sum of the angles beta created by the transformed line. So what we're doing, we're setting, so what we need is to set this threshold. But instead of setting a specific threshold, what we're going to do, we're going to set the threshold to be pi. And this will enable us to use the convex hull to construct all those curves instead of computing for every single point its two special points. Now, this observation is important and is the only reason that this operator is efficient. Let me mention a few of the theorems that we proved in the paper. And the first issue regards correctness in the limit. That is, correctness when the whole set of points, the whole surface, is given. In this case, lemma 1 claims that every point that is marked visible by the HPR operator is indeed visible from C. Or in other words, the set of points that are marked by the operator is contained within the set of points that are really visible from our point C. The second lemma claims that when R approaches infinity, then the set of visible points marked by the HPR operator is equal to the set of visible points. Or in other words, together, what these two lemmas claim are that our operator is conservative and converges to the correct solution when R approaches infinity. Unfortunately, in real life, we don't have the whole surface, and then it can no longer be true once we have sampling that the set of points marked visible is really contained within the set of visible points. So we have to define a more practical visibility. And to do this, we define epsilon visibility. We say that a point is epsilon visible if there exists some Q whose distance from P is less than epsilon, and Q is visible from C. Or in other words, we say that a point is epsilon visible if moving it in a distance shorter than epsilon will make it visible. And now, when we have this epsilon visibility definition, we can extend the theorems that we have, or that we proved before. And now we can say that for sufficiently dense sample, the first theorem claims that for every R being the radius of the bounding sphere, there exists some epsilon such that every point that is marked visible is indeed epsilon visible, and vice versa. For epsilon, there exists R such that every point marked visible is epsilon visible. But these theorems are interesting not only in the way they are put here, but also it's interesting to follow the proof, because the proof itself shows that there are interplay between three different parameters, between epsilon and R, as we see here, but also with rho, the density of our sampling. And it turns out that as rho becomes smaller, that is, our point sum becomes denser, then a smaller epsilon can be obtained. So this is the first part of my talk where I discussed the operator. And let me move on to the second part where I'm going to present a few applications of this operator, visualization, reconstruction, and shadow casting. So the first application is visualization of point clouds. We would like to visualize our raw data, for instance, during long scanning sessions, in CAD applications, in some simulations. And this is the bunny from last night, and it's hard to know whether this bunny is looking forwards or backwards. And in fact, I got different answers from different people. After applying the operator, it becomes evident that it's looking backwards. Here's another example. This is the dragon, and you can see that there is a whole mass here in the face area. And here you can see both visible and invisible legs. After applying the operator, we get a much cleaner dragon. This is David again. You see front features and the back features. After applying the operator, this is what we get. And in the paper, there are many more examples. Here's one example that is interesting because it's a very dense sampling of a jet fighter. And you can see that after applying the operator, for instance, from every ring of points here, you get only a sub-ring, which is the subset of the visible points. And this example illustrates the power of the operator, where it manages to extract the visible points, even when in cases where the alternative of reconstructing the surface might fail. The second application is view-dependent reconstruction. So in this case, what we're doing is, when we apply the operator, we transform the set of points, and then we construct the convex hull, and until now, we just use the points that fall on the convex hull. So now instead, we also use the triangles that that build up the convex hull, eliminating some long threshold triangles. And this is the result that we get. And you can see, you can understand that we didn't increase the complexity at all. It's still order of n log n because we had to compute the convex hull anyway. Here is another example. And we said that this reconstruction, we call it a quick and dirty reconstruction. It's quick because the operator can perform say for 200,000 points, it would take a second. For 500,000 points, it will take something like 4 seconds. And comparable to other reconstruction algorithms where they operate on the same point set, it may take a few minutes. But it's also dirty in the sense that you're not going to get the same beautiful surfaces that you're going to get if you get the full reconstruction. And just to illustrate what it means, what we mean by view-dependent reconstruction, let me show you a short illustration. So this is the input point cloud of Bimba, and this is what we get after we apply our operator. And now we're going to apply this view-dependent reconstruction. So this is Bimba after reconstruction. We're going to change the viewpoint and reconstruct the surface every time again. And now we are going to hold the viewpoint and just rotate the input, the surface, so you see what it means to be view-dependent reconstruction. So you see here that nothing was reconstructed on the back. You get the reconstruction only for the parts you actually see. Okay. Our third application is shadow casting. So what we do here, we put a light where we have the viewpoint. And now we apply our algorithm, our HPR operator, only on the vertices of the mesh. So we compute visibility only on the vertices. Once we computed the visibility on the vertices, we interpolate it along the faces of the mesh, and this is the shadows that we get as a result. And here is another example, again, having only one light. It's marked here, but of course we can use any number of lights that we wish to have. And you see that really the light manages to penetrate the holes of this surface. This example compares our algorithm to the result that would be obtained with exact visibility. That is, if the visibility was applied on the faces of the mesh. And you see that the results are not identical, but they are good enough. So let me conclude. So I presented to you today our operator, the HPR, the hidden point removal operator, that is very, very simple. It can be described in a few lines and can be easily implemented. And we did it in MATLAB in really using very, very short code. Its complexity in 2 and 3 dimensions is order of n log n, but it can be extended to any dimension. I showed you that it works in dense as well as sparse point clouds. We proved its correctness in the limit and gave some theoretical guarantees for the case of sampling. And we believe there are many applications that can benefit from the operator. But today, we showed 3 applications: visualization of point clouds, view-dependent reconstruction, and shadow casting. Thank you.
Thank you. I will again start with a few questions and then hand it off to the audience. The first thing that I was wondering about, when you showed these view-dependent reconstructions, maybe you can elaborate on this. Let's suppose you would have reconstruction from infinitely many viewpoints. Could that relate to some kind of surface reconstruction algorithm that we know? Is there some? Do you have insights on that?
Actually, it's a very interesting. It's a very interesting direction. So maybe I'll elaborate a little bit on your question. So the question is, because there are reconstruction algorithms that are actually using Voronoi diagrams, the question is, how is this convex hull, which is, of course, connected to Voronoi diagrams, will relate to these reconstruction algorithms? I guess this is the question. So let me answer this on two levels. The first is implementation, and the second is the theoretical parts. Implementation-wise, we've tried to do it. We've tried to reconstruct it from various points and to see what we get. And the hard problem is the stitching. So it's not that trivial to do it. On the theoretical point of view, which is maybe even more interesting, how these things compare, lately we start thinking there is a connection. If you replace your inversion function. But we don't have results yet. But because you don't have to stick to this inversion function. It's general enough. Any inversion function with several properties can do well. So we do think there might be a connection to these reconstruction algorithms.
So you're saying if you find the right inversion function, then it would correspond?
It might. It might.
Okay.
But it's certainly like a very interesting direction that we are pursuing. Yeah.
Okay, thanks. The other question I had was that in your example, you only showed point clouds that were sampled from, nice meshes, and there's no noise, no outliers. Have you tried your method on raw scans where you have these artifacts? What happens in this context?
Yes, so we didn't deal intentionally with noise. We just, whatever the input is, this is what it's going to visualize. So I guess if you want to, you can use some noise reduction functions if you do wish before you use it. But really the problem is how convex are doing with noise. That's the basic problem. And I was looking a little bit at computational geometry papers. I haven't found convex hull with noise, but I did find medial axes, which are highly connected, that are handling noise. And I guess that if we want to go to this direction, this is really the place to put it. Convex hull with noise should solve the problem.
Okay, thanks. I have one question from Florent Duguer. I hope I got the name right. And he's asking, there seems to be halos around the edges, such as the dragon's cheek and David's left hand. Do you have insights on these halos or those artifacts?
Like the silhouettes?
In the silhouettes, yes.
Okay. I'll show another slide, because I have another theorem that... Oh, this is the one. I put some other slides for the questions. So we have another theorem that I didn't quote in... that I didn't put on the slides, because it's a bit... I don't know, maybe more complex. And this is a relation between R and the local curvature. And what this lemma claims is that there is a connection with the curvature. That is, we mark P visible if and only if the curvature satisfies this formula, which means that for convex sections of the surface, we're always going to find the right solutions. If there's a concave, then it means that the curvature should be low enough for us to find the visible points. But according to the lemma we had before, then if R approaches infinity, we're going to find all those truly concave pieces. So this is where we might see artifacts in deep concavities and, of course, near the silhouette. However, if we enlarge R enough, at least in the continuous case, we know that we're going to find the exact correct pieces. Of course, like intuitively, why is it that we get wrong maybe visibility marking near the silhouette? Because then moving the point a little bit will transform it from visible to invisible. Okay, so this is the intuition for why things happen.
Okay, are there any more questions from the audience? Please step up to the microphones. Okay, well, if this is not the case, let's thank our speaker and all the speakers of the session.